Hi, my name is Junhyuck and my partner's name is Guoru Xiao. And right now, I'm going to be performing a quick demo of our Lab0 of our CS152B class. Before we begin, this demo is structured in a bottom-up format, starting with our testing and waveforms, moving into our design and implementation, and ending with our conception and detailed approach, and even a couple schematic designs. This is in such a way that at any point of the demo, if you believe that you've seen enough or you like to read it instead of watch it, then you can save yourself some time and close the video. So without further ado, let's get into my Xilinx ISE. And we're going to be starting with the BCDCounter test bench, as alluded earlier. Nothing's too special about this test bench, apart from the fact that we have a register correctness. And this correctness register should always be 1, and a register 3-bit register called test, and this is just to check what number test we're on. Initially, we're gonna begin by setting every input to 0 except for clear. Clear is going to be set to 1 because when clear is low is when we're actually going to be doing the asynchronous clear. Test 1 is trying to load 7 into our queue. Test 2 is trying to load 7 into our queue, but having clear set to low, so that should override our trying to load. Test 3 is a simple increment from 0 all the way to 9, and these if conditional statements are just to see if indeed everything is working properly. Test 4 is decrementing from 9 to 0. Again, no carryout yet. And test 5 and 6 is our carryout output test. And in test 5, we increment from 9 all the way to 0 and check that the carryout is indeed turning on. In test 6, we decrement from 0 into -9, or 0 into 9, and we're checking the carryout is true there. And without further ado, let's try looking at the simulation waveforms. So BCDCounter test bench, and let's simulate this behavior. Immediately, I'm going to be changing these radixes into unsigned decimals for D, Q, and test. Just make it a little bit easier to see. Let's zoom out and then zoom in a little bit. Starting with test 1, we see that 7 is indeed loaded from D. Starting test 2, we see that the asynchronous clear occurs at once the clear is set to 0, even though we are indeed trying to load 7. Test 3 is our increment from 0 all the way up to 9. Test 4 is our decrement from 9 all the way down to 0. At this point, actually, we're in test 5 and we're loading the value 9 into the queue. So this isn't actually decrementing into 9 yet. Here, as 9 is loaded up, we're actually going to send the increment signal in, and notice that the Cout is indeed set to high. Notice how our correctness register is set to high across the board. That means we know that basically our test is indeed working properly. Test 6, we clear it, and then we're going to be loading in 0, but we already cleared it, so loading in 0 is the same thing. Q won't change. And then we're decrementing it from 0 into 9, and notice that the Cout is indeed being set to on. So everything is working properly there. Next, we're going to be looking into the test bench for divisible by 3, and this is where it becomes interesting. We have a register, a 14-bit register called number, which basically is the binary representation of the 16-bit 4-digit BCD number. We also have a 4-bit test number, which is basically going to be indicating what test we are on. We're testing a couple of numbers here. We actually have a clock register here, but that's not being used at this point because we're testing the combinational logic of it. We actually have a sequential logic implemented as well using conditional statements, but we're not going to be looking into that. We're testing inputs of 3, 0, the minimum, 6, 3609, all of these divisible by 3, 7485, and 9999, which is the maximum. We're also testing a couple of non-divisible by 3 numbers, 1, 301, and 9998. What we should see is the output go from high to low for the last 3. And if we simulate it, and quickly I'm going to be changing the radix of our test as well as our number here. The reason why we have number, by the way, is because we can actually change the radix of this 16-bit into an unsigned decimal. It'll give us a weird number because This is Xilinx iSIM. Doesn't of course have a representation of a specific 4-bit, 4-digit, BCD number. So we see that for 306, 3906, 7485, and 9999, we have an output that is high. Consequently, and afterwards, we have a output of 0 for 301, and 9998, which is of course the correct output. Moving on into divisible by 11 test bench, it's pretty much of the same thing, except we have a couple more test cases because this is a bit more difficult to check. 0, 1, 11, 111, 0, 0, 0, 0, of course our minimum again, 9999 our maximum, 5786, which is also divisible by 11, and then a couple of numbers that are not divisible by 11, 1, 12, 8108, 9998, and 2 more numbers that are divisible by 11. This is just because we're trying to test the computation of a minus b plus c minus d, because the outcome possibles are 11 and negative 11. So 1 is for 11, 9 plus 2 is 11, and 1 is for negative 11. 0 minus 9 minus 2 is 11. We should see that it dips from high to low, and then for the last two goes back to high. Converting these back to unsigned decimals. I really should save these configurations, but I am much too lazy. Zoom out and then zoom back in, and we notice that for test cases 0 to 5, 11, 111, 0, 9999, 5 to 7, 8, 9, or 8, 6, we have a high signal for the output. For 1, 12, 8, 108, and 9998, we have a low signal, meaning that it's not divisible by 11. And lastly, and thankfully, for 902 and 9020, we have a positive output, meaning that indeed everything is working properly. Now let's backtrack a little bit and talk about the implementation for our BCD counter. And actually, as I pull this up, the BCD counter was actually rather easy to implement. Because we're allowed to use conditional logic, and because this is a sequential circuit, the final design is rather similar to what one would see in C code. Firstly, we implemented a simple if statement to check for the asynchronous clock inside our always block that activates on the positive edge of clock and the negative edge of clear. Again, negative edge is a little bit weird, but when clear is 0, as per described by the specification, we're trying to be doing the asynchronous clock. Before doing anything else, we're just doing the asynchronous clock, and then this is our conditional logic. Load 1, enable 1, we're just going to load D into Q. Load 0, enable 1, and up 1 means we're incrementing, and we have the carry out implementation included within this if-else block. Lastly, if load 0, enable is 1, and up is 0, we're decrementing, and of course we have the carry out logic implemented here as well. So nothing too rocket sciencey. And now is the fun part, and that is BCD divisible 3 and BCD divisible 11. And before we begin that, one thing I wanted to note is Bob and I, or Guoru and I, we've worked extensively together on the sum modules, but we've decided to actually split paths and do the part A and part B of part 2 separately in order to show completely two different kind of styles of coding that both work and are both pretty cool actually, but is intended for different uses. My implementation of BCD divisible 3 is actually very abstracted, and what that means is I have one instantiation of sum, which is an instantiation of the sum module sum of 4, and test, which is an instantiation of divisible 3 6-bit. Before that, I'm actually separating the 16 bits into separate 4 bits for each single digit. And of course, sum is an abstracted version where somehow the 4 digits are added together into this value called sum temp. And in test, we have the sum temp somehow evaluating into an O output. So that's one way of writing it. And next I'm going to be showing BCD divisible 11, because explaining the logic for that, it will actually help me explain to you the logic for divisible 3 6-bit instead of 0 to 36. And I'm going to be explaining 0 to 36 as well. Which is our first implementation. Divisible by 11, which was done by Bob, is actually a very beautiful code as well. This is the sequential version of it, and including like assignment operators and stuff, just to see that everything's working test bench wise. And here is the actual heart of the code. And at first, setting sub digits is actually identical to what I implemented, but then we have these beautiful local parameters of 0, 1, 11, and negative 11, which is really cool. The assigning digit is the same, and here is where the computation comes in. And the computation here is we're going to be counting the number of odd and number of even sums. So basically, the sum of two SOT0 is adding digit 3 and digit 1. Sum of two SOT1 is adding digit 2 and digit 0. These are both instantiation of one submodule called sum of 2, which I'll get into later, but spoiler alert, it is a 6-bit ripple carry using full adders. And then we're actually seeing the subtraction via adder, which basically means we're going to be inverting the digits of the sum right here. We're going to be adding 1 to that, or this adding 1 is actually at the end, but either order works. And then we're going to be adding all of that to odd digit sum. And what that does is by adding one regular number and one inverted plus 1 number, which is a complement, 2's complement, we can actually produce a subtraction rather than an addition with the same adder. Lastly, we're going to assign O, the output, to whether or not that outcome is equal to 11, negative 11, or 0. And I actually really like this implementation because the way it's set here and using local params means that I can actually change these values into anything I want very relatively easily. Just find the number and just implement it there. Looking into sum of 2, and I'll be finding that using files. It is indeed a pretty simple full adder, 6 single bit full adders rippling into each other. Let's carry out to carry out, carry out to carry in, carry out to carry in, and that's how this sum of 2 6-bit ripple carry is produced. For my implementation, however, we see yet again, I'm going to be going back into sum of 4 and divisible 3 6-bit, but sum of 4 is basically 2 4-bit ripple carries and 1 8-bit ripple carry. And that 8-bit ripple carry is actually 2 4-bit ripple carries, going from COtemp to CN here, and that's where the ripple happens. And in the 4-bit ripple carry is my implementation of 4 different 1-bit full adders. And lastly, we're going to be talking about full adder, which is a very simple, very easy to read logical code that includes 2 AND gates, 2 XOR gates, and of course our final OR gate. The schematic is going to be shown later. The key difference actually with this is that because of how this is abstracted, we do know what's happening from a bird's eye view, but we don't actually know what's happening in specifically divisible 3 6-bit. And that's what I'm going to be explaining right now. And what might surprise you is that the logic for divisible 3 6-bit is identical to the logic in divisible 11 by chance or by specific reason. After researching how we can determine if a sum, a binary number, is divisible by 3, we noticed that the same computation that we done for a base 10 number and base an 11 divisibility, which is the a minus b plus c minus d, can be applied to any base x number and divisibility by x plus 1. And coincidentally, we're trying to check if a binary number, base 2 number, is divisible by 3, which means the same logic applies. We're going to be counting the even number, even bits, and the odd bits, doing a 2's complement, adding them together, and seeing what the result entails. That's occurring over here. First, I'm going to be counting the odd bits and the even bits, and I should have used a submodule here, but I didn't want to because it's very simple code. This is a half adder, and this is actually a full adder, and because it's just 2 digits, it's literally 2 lines of code. I didn't want to make a separate submodule. We're actually going to be inverting the sum of evens. we're going to be adding 1 to it using the 6-bit ripple carry. And then we're going to be adding the sum of odd to the inverse add 1, which is the 2's complement. Lastly, we're going to be taking that and putting it into a truth table to see whether it is indeed a multiple of 3 from -9 to 9. And that's only 7 numbers. Before, we were thinking about how we could do this. And one of the implementation that I ended up with is actually what was commented earlier, which is 0 to 36. We noticed that because this is a 4-digit 16-bit BCD input, the maximum sum of the digits can only be 36 and the minimum can only be 0. What you can do after that is just have a huge truth table that just tracks whether it's any multiple of 3 within 0 to 36. But of course, this isn't scalable, and even though there's a lot less lines of code, I believe that this is a much more easy to understand and scalable, more elegant way of trying to determine if a binary number is divisible by 3. This is still not really scalable, but it's good for actually quite a bit of digits. It should be. But yeah, that's basically the implementation of all that. I did counter as well. So next up is we're going to be looking at a couple of the schematics for some of these. Let's start with BCD divisible 3 and set that as the top module. And view an RTL schematic of this, which is a generated schematic. I'm actually at this point trying to change it to float, and yes, I do want it to be top level. And we see this simple BCD divisible 3 input is 16-bit and the output is 1-bit. If you delve deeper into that, we'll see that it is comprised of a sum of 4 and the divisible 3 6-bit. And of course, we see this abstraction coming into play now when we look into the schematic and the development of this, or the generation of the schematic. Sum of 4, delve deep into it, is 4-bit RCs, 2 of them, and an 8-bit ripple carry. Delving deeper into the 8-bit ripple carry is, of course, what we see is our full adder, and this is also abstracted into a mux or an XOR. That's a mux, I believe. But actually, one of these is indeed going to be showing a more traditional view of a full adder. And even this is a little bit difficult to see. So I've created this quick demo of how this design that's generated identically translates into a more familiar form of the full adder. So we see that just by rearranging these XORs and the ANDs and adding the wires, we see that the implementation is almost identical, or is identical to a traditional full adder. Pausing it here, we see inputs A, B, and C in will result in a sum and a C out. So I think that's pretty cool. Going back out and into the divisible by 3 logic, we see a little bit of confusion, but we see the sum of 2's here, as well as a series of 7 AND gates and the final OR gate. And this is indeed our truth table, trying to determine whether this number that we've ended up with is indeed divisible by, or is indeed equal to any multiple from -9 to +9, which is 7 numbers. Moving on into the schematic for divisible by 11, because all of this is actually, sorry, let me just set as top model. And because all of this is indeed in one more explained top module, we're going to be seeing a lot of, I would expect, sum of 2 implementation. And indeed, we see a lot of those. So these are the 4 sum of 2's that are used to calculate the sum of evens, sum of odds, and then complement, add 1, and then, or sorry, this probably add 1. Oh no, SO2, oh wow, it actually labeled all of them. So we can actually trace back into what it is if we wanted to. And we see right here SOT3, which is the adding 1. And indeed, this is the SOT, which we're adding 1. And lastly, a series of 3 AND. This is actually, I believe, an AND gate, just expanded a bit. a series of 3 ands and an or. And that basically is testing -11, +11, and of course 0. And this design is admittedly a lot more easier to read, but a lot less abstract, of course. My design is easy to read until you start delving in, and then it's difficult to read. But yeah, lastly, we're going to be looking at the schematic for BCDCounter. At this point, I'm not sure if you're still listening, but if you are, then thank you so much. But the BCDCounter schematic isn't much to look at, to be perfectly honest. And let's look into this huge truth table. And what we'll notice here is that because the code is actually simply a series of if statements and conditional operators, the schematic is slightly difficult to decipher. Nevertheless, we see a couple of muxes that actually control the conditional statements, and they clearly outline into the traceable back inputs, which is right here, the clock, clear, up, and enable. So yeah, that is the entirety of our demo. If, again, you've listened to this far, then thank you so much. And that's about it.